In our next section, we're going to look at our inter-AS L3VPN and how we can do path selection modification, that if we have multiple links between the providers and we want to choose one as a primary path or a secondary path on a per customer basis or on a per PE basis, which is not to be confused with the actual MPLS traffic engineering feature, MPLS TE. In this case, we're simply talking about changing BGP best path selection, but this is going to be for an inter-AS design. Now, if we take a look back at our current setup, we right now have a BGP peering that is going between a router 3 and XR3, and this is our IP version 4 BGP plus label peering. And then we have our multi-hop VPN v4 session that is going between router 1 and XR1. Now, if we look at how we are currently sending the traffic when we go between the providers, like let's say we were to go to router 10 and we were to do a trace route to its other customer destination. Let's look at the show IP route, and the destination is 8888. Right now we're using the inter-AS link that is between router 3 and XR3 because this is the only eBGP peering that is happening directly between the devices. Basically, it's the only physical link. So what we're going to do next is to add another physical link, another physical peering between the autonomous systems, and then see what happens in terms of the inter-AS path selection. So specifically here, we're going to do this peering between now router 3 and XR2. So from router 3, if we take a look at how are we currently doing the peering, let's go to router 3 and let's look at the show run section BGP. We have this IPv4 unicast peering that's going over to XR3, and we're sending a label value with it. Again, the key point here is that in order to do label switching between the customer's sites, we need to make sure that the next hop is reachable via a labeled path, and this is what the BGP Plus label is doing for us. Someone had asked the question, is what RFC this is related to? This is called RFC, it's 3107, is carrying label information in BGP. So it's the combination of this plus the previous one that I had mentioned, which is number, It is number 4364. So the other one, 4364, is BGP IP MPLS virtual private networks. So in this one here, this is where it defines what are the different options. So it's under multi-AS backbones. And in this case, we're doing option C, which is VPN IPv4 routes, but we're using BGP plus labeling between the ASBRs. And I believe in here it should be calling 3107 within this document, which is this one, carrying label information in BGP v4. So it's basically a combination of both of them together is this current solution. Okay, so next we're going to do a peering between router 3 and XR2. So let's make sure we can reach that. It's going to be 10.3.12.12. And I believe that interface is currently disabled. So let's look at from router 3, the show IP interface brief. And yes, it's down. Okay, so let's go to gig 1.312 and no shot. And on XR2, let's check that likewise. Show IPv4 interface brief. Okay, it's enabled on that side. So let's go from router 3 and then let's do a ping to 10.3.12.12. Okay, we have reachability. So we can essentially take the same type of BGP config that we have and then just apply it onto the other neighbor. From the remote AS point of view, though, between router 3 and XR2, or XR3 and XR2, we do want to be running a regular IPv4 labeled unicast pairing between them, because we need to make sure that if we're doing a path selection change on one of them, that it is affecting the other device as well. So with your typical BGP design, that if you have two provider edge routers, there's two basically border routers. So we have basically border router 1 and border router 2 that are going to a different BGP peer. You want to make sure that you have an east to west cross connect between, or east to west peering between these two, so that they make sure to agree on what the best path selection is going to be to exit the network. Okay, otherwise, since we would have to do redistribution of BGP into IGP on both of them, we could have potentially a situation for a routing loop. If I say my IGP route is to you, but then you say your BGP route is to me, then we could bounce the traffic back and forth. So it's the same type, and this doesn't really relate to MPLS. It's the same type of design as you would have in just regular unicast routing, that you have multiple points of redistribution. You just need to make sure that both of them agree on whatever the exit point is going to be out of the AS. But in terms of router 3's config, nothing else really changes here in terms of BGP other than we're just adding a new peer. Okay, so the peer is going to be 10.3.12.12. Okay, same remote AS, and then we're going to activate the neighbor. So neighbor is 10.3.12.12, activate, and we are also sending them a label. Okay, if we go to the other side, let's go to XR3 and look at the show run router BGP. And this is basically the same type of config we're going to do to from XR2. So let's go ahead and make some changes to this. We're going to say that we're still advertising the network 11. Okay, we're going to need to do this on both points. And the neighbor is 12.3. And then basically the rest is the same. Okay, we just I need to add that route policy as well. So let's look at the show RPL. And we have this route policy pass. Okay, so let's go ahead and commit this config on XR2. And next, let's look at the show BGP, IPv4 labeled unicast summary. And we see that we're receiving 3 routes that are coming in from router 3. Since it shows up under this output, it means that these routes do have labels included with them. So we'll see that in this particular example, there is a key difference in the output of show BGP IPv4 unicast and show BGP IPv4 labeled unicast. Okay, if we look at the unicast summary, we see that there are no prefixes being learned in that don't have labels, but there are 3 prefixes received in that do have labels. And we'll see in a minute why this is going to be a significant change. Okay, also under XR3, if we look at the show run router ISIS, we were doing redistribution of BGP into ISIS. We're going to need to do the same thing here on XR2 because the device that has the BGP best path, that's the one that we want it to be originating the route into IGP. So if we basically just need to take this config and then apply it on XR2 as well. So on XR2, if we look at the show run router ISIS, we're going to say under router ISIS 1, under address family IPv4 unicast, we're going to redistribute BGP 11.12.13. Okay, if we now look at the show, let's just look at the show IP route and look at the global table, and we should see that we have these BGP routes that are being learned in from router 3. Okay, so now let's look at how did this change the path selection in terms of the actual traffic flows between the devices. So let's go to the end customers. Let's say we're looking at this from router 8 and router 10's perspective. So on router 8, we're going to do a trace to 10.10.10.10. And the route is going to 11, and then it's dying. Okay, so let's make sure that this is related to the BGP peering that's between those devices. So what I'm going to do is just a temporary troubleshooting mechanism. I'm just going to shut the link down that goes from XR2 over to router 3. Let BGP reconverge, and then we'll do the trace route again to see if adding that new peering is what actually broke the data plane. So let's go to XR2 and let's say on interface gig 0000, this is 312. We'll shut that down and commit. And then on router 3, likewise, shut down the same link gig 1, 3112, shut. Okay, if we now trace again from the customer, which was router 8, now traffic is flowing. It's going from 11 to 12 to 13 to 3 to 2. So right now it's going in this direction from 3 to 2. Okay, so that's the destination. But when we enable this peering between these two, something is breaking in the traffic flow. So before we can change path selection and say I want to prefer one link over the other, we need to make sure that the flows are working both ways. So a simple way to test this is just disable one of the links, make sure the traffic falls over, then change which one's disabled. So enable the link between XR2, router 3, disable the link between the other two, and then see if that is going to allow the traffic flow likewise. So what I want to change now is to shut down this link and enable this one and see if we're able to get traffic to go through. So on XR2, we're going to just undo our last change. So we'll say roll back the config, last one change. That's going to unshut the link. Then on router 3, we're going to no shut gig 1 312, but we're going to go to gig 1 313, and that one is going to get shut down. Okay, same thing on the other side. So on interface gig 0000313, that's shut. Okay, let's now see from router 3's point of view, if we show IP route, we should be learning the remote loopback as a BGP prefix. Okay, let's see if we now have connectivity. So let's go to 8 and let's do a trace to the destination. No, we don't. Okay, so this means that definitely the traffic flow is broken because of this new peering that's going from XR2 over to router 3. So next thing we need to look at is we need to trace the label switch path on a hop-by-hop basis and figure out where specifically is the break. Now we could do this by looking at it in the data plane and doing some packet captures, but within the scope of the lab exam, you're not going to be able to do the captures and get access to Wireshark. So we're going to constrain our troubleshooting just to the CLI for now. Okay, the first thing we want to know is that from the customer router, so from router 8, is it learning its route with the PE to CE routing protocol? And this is one of the easiest problems to troubleshoot, because if you're not learning the route, then you know you're definitely not going to be able to reach it. But in most cases like this, when we're dealing with inter-AS L3VPN or carrier supporting carrier, what makes it a confusing problem is that the customer is learning the route, but it's still not able to reach it. Okay, so we see that we have the destination 10.10.10.10 on router 8. If we go over to 10 and show IP route, we should have the route to 8888. That's not the problem. So it's not an issue in the control plane. There's some sort of problem in the data plane. Okay, the next thing we need to look at is how is the customer learning the route? So from 8's point of view, it says the next hop is .11. Okay, there's only one PE router currently. So we need to go to 11, which is XR1, and see how is it learning the route. If we show BGP, VPN v4 unicast, it's currently getting the destination, which is router 10. It's learning it from VPN v4 BGP, and it says the next hop is 2222. So let's look at the show BGP, VPN v4 unicast. The route distinguisher is 200, 200. That's the one that we're importing it into. And the destination is 8888/32. Okay, also notice now here that the VPN v4 session between router 1 and XR1 went down. So it means that there's definitely a transport problem between the ASs. We don't necessarily know what the problem is yet, though, but adding that new peering broke the control plane of VPN v4 BGP. So eventually we should see here that this route is going to disappear because the route was not 8888, it was 10.10.10.10. It's no longer there because now the session is down. So next thing we need to look at is why did the session go down? Why am I not able to reach between XR1 and router 1 when I'm using this, this next alternate peering? So let's look at next, do we have a route to the remote loopback? Okay, it's 1111 in this case. Okay, we do have a route to them. And let's do a ping to 1111, sourcing the traffic from our loopback. Okay, this is where we need to establish the transport between. So it's definitely related to this. Okay, next thing we need to look at is how are we learning this in terms of our internal routing. Here from XR1, we're learning this from ISIS. So if we look at the show IP route for 1111, it says the next hop is 10.11.12.12. Now, this problem shouldn't necessarily directly relate to label switching because all of the devices in the transit path here should already know this prefix. So we need to look at troubleshooting regular IP routing before we look at troubleshooting MPLS. So next we need to go to XR2 and see how is it learning the route to go to router 1. So from XR2, let's say show IP route for 1111. It says I'm learning this through eBGP, and specifically it is a labeled unicast route. Okay, next hop is 10.3.12.3. So if we go over to router 3 and say how do we get to 1111? Okay, I know this from OSPF from router 2. And if we do a trace from 3 to 1, intra-AS reachability is there. Okay, if we go from XR2, since we're not currently advertising that transit link into IGP, we would not be able to test whether that's the problem in terms of the connectivity. So next step, if I didn't know where to go next with troubleshooting, what I could try next would be to advertise this link into OSPF and then see if I can do a ping from XR2 to router 1. So let's try that here. Let's go to router 3. And on this interface, which is gig 1.312, let's say IP OSPF 1 area 0. And we'll then do a ping to 1111 and source the traffic from 10.3.12.3. Okay, router 1 does have a route back to this link that I just advertised. So if we do the same thing from the other side, from XR2 is to ping 1111, says it's unreachable. Why would this be the case? Okay, there's something key in this output that's telling us here how does XR2 have to reach this destination? It says it's known via BGP. Distance is 20 because it's an external route. The AFI is what? AFI is labeled unicast. So it means we have to do MPLS switching towards this particular destination. If it was a regular unicast route without a label, we would be sending it as untagged traffic, as regular native IP. So what did I not fix on XR2 that I had previously fixed on XR3? And again, this is a real easy problem to skip over because it's not something that you would normally think you need to do. If we go back to router 3, and if we notice when we formed that new peering, it gave us a hint to what the problem was, that I didn't add the static route. So for every inter-AS link that we have, XR needs to have a static route to the other end in order to do the label switching towards the destination. But again, router 3 is natively fixing this because when it does MPLS BGP forwarding, it automatically adds the connected /32. Okay, so on XR2, I need to make sure to add that in. So let's say under router static, address family is IPv4, and the IPv4 unicast, and then the destination is this. Okay, that /32 is reachable via gig 0000.312. Okay, so let's now see, can we now ping 1111? Yes, we can. Okay, this should now mean that XR1 can ping 1111 when we're sourcing the traffic from 11. Okay, we can see the BGP neighbor comes back up. If we go back to router 8 should now relearn the IGP route, so it has 10, 10, 10, 10. And let's ping to the destination. Okay, so now we have reachability both ways. Okay, next we want to look at Well, what happens when we bring up both inter-AS links? How is it going to make its decision of, are we sending the traffic directly from XR2 to router 3, or are we going to use that link that goes from XR3 to router 3? So let's go to XR3 and bring that interface back up. So I'm just going to do a rollback. My config last one change. That's going to unshut the link. And then on router 3, likewise, this is interface gig 1.313. Okay, so now from router 3, if we look at the show IP BGP summary, we should see we're going to have two different peers. And we should see here shortly we're learning the route both ways. Okay, so now let's do a trace. Let's do a trace from router 10 and see how are we going to go to get to router 4. So let's ping, or no, this is from 10. 10 is in the VRF with 8. 8888. And let's do a trace to 8888. Okay, so currently we're going from 2 to 3, 2 to 3, 3 to 12, and then 12 to 11. And then to the destination. Okay, let's see if this is also true as we're coming in from router 7. So from 7, we'll trace to 4444. Same direction, 3 to 12 to 11 to router 4. Okay, now if we look at this from router 3's point of view, we see that there's only one route that we're learning from IPv4 unicast BGP, which specifically is the loopback of XR1. So if we look at the show IP BGP, the best path selection that we're making here ultimately impacts the VPN v4 forwarding, or the L3VPN forwarding that is inter-AS, because the route recursion to the BGP next hop is ultimately how we choose the label switch path. So what this means is that if we want to influence how traffic for VRF-A is routed, what we need to influence is how is the next hop routed. So changing the VPN v4 attributes itself are not going to do anything. If we were to go to router 3 and say, when I'm learning the BGP VPN v4 route, change the local preference or do AS path prepending, that's not going to affect anything. Because ultimately when router 3 makes this decision and we show IP route VRF-A, it's going to say, well, I know how to get to 4444. It's via 11.11.11. So if we look at the show IPsef for VRF-A to say, how do we get to 4444/32? It says, well, you have to recurse to 10.3.12.12. The reason why is that the next hop for 11 recurses to that. So it doesn't directly tell us that these two are related, but the combination of the global routing table plus the VRF table is going to tell you why the ultimate forwarding decision is made. So since 4444 is via 11.11.11, 11.11.11 is via gig 1.312, it means through the recursive principle, 4444 is also via that interface. Okay, then specifically we're using that label as the transport label to get to this destination, and then the final VPN label is 16,000. Okay, let's also look at this from the reverse path. Let's say we go from 8 to 10 and from 4 to 7. Okay, those are the two different VRF destinations. So 8 does a trace, it's going through from 12 to 3. 4 does a trace, it's going same path. Okay, it's going 12 to 3. So let's look at from 12's point of view, why are we choosing this particular path? If we look at the show IP route, we have the remote loopbacks being learned as eBGP routes. So 2222, 3333, this is ultimately influencing the path selection. Now, as I mentioned before, one of the things that we would also want to do is enable an iBGP peering on the east-west link between XR2 and XR3. Because why? Okay, let's say we were to leave the design as it is now, and we want to reroute the traffic. Let's say we want to reroute the traffic so we don't use the link between XR2 and XR3. Let's say we want to go this way. What would be the problem from XR2's point of view in making this path selection change? Well, let's think about how is it learning the route. Okay, from router 3, it's learning the route as what? As eBGP. From XR3, it's learning the route how? As ISIS. Because I didn't enable a BGP peering between the two of these. So if we were to leave the network as it is now and want to change the path selection, the only option we would have would be to change the administrative distance. Because we're comparing eBGP with a distance of 20 to ISIS with a distance of 115. Now, if we were to enable an iBGP peering, though, we could make the best path selection decision before we go to feed the route from the BGP rib to the actual rib, to the routing table, and then administrative distance wouldn't necessarily come into play. Okay, so next step is we're going to do a peering between router 2 or XR2 and XR3. Okay, so let's say that we show run router BGP. And it's basically going to be the same thing, except this is going to be an iBGP peering. So we're going to go to router BGP 11, 12, 13. Neighbor is, we'll say the loopback, it's going to be 13, 13, 13, 13. The remote AS is 11, 12, 13. Update source is, dash source is loopback 0. And then the address family is both IPv4 unicast and labeled unicast. Okay, I'll explain in a minute why I'm doing both of these. Let's show our config and then commit. Okay, the other one is going to be the same thing except the different address here. It's going to be the loopback of 12. So 12, 12, 12, 12. Okay, so next let's look at the show BGP IPv4 labeled unicast summary. And we should see here that we now have the peering that goes over to 12. Okay, and also we're learning prefixes. So next let's look at the global BGP path selection rules. And let's say that we want to make the change outbound one direction and then inbound the reverse direction. So let's say that we want to modify this, and let's make sure that it's still going in that direction. Which from, let's go to router 8 and trace to 10. Okay, we're going the same direction. We're going 11 to 12 to 3 to 2 to 10. Let's say that we want to modify this so it goes 11, 12, 13, then 3 to 2 to 10. So we want to use the alternate inter-AS link as opposed to the one that is the default decision. So if we're making the change in order to choose basically this link as primary and this link is secondary, then whose decision are we trying to modify here? Okay, and part of this has to do with XR2 being in the path of the data plane for XR1 to get to XR3. Okay, the design would be a little bit different if we had another cross connect that went between these two. But let's say just for this particular example, we're just going to leave it as it stands. So it means it's basically XR2's BGP best path selection that is what is making us go directly to router 3 as opposed to go to the other potential provider edge router. So let's look at from XR2's point of view, how specifically is it making this decision? That if we look at the show BGP, VPN v4, or not VPN v4, in this case, this is IPv4 labeled unicast. And we want to know how are we going to 2222. Okay, because this is the endpoint of the LSP. That's what we're trying to change the path selection to, the 2222 address. And it's going to be for 2222/32. It says that we have two available paths. The first one is the best path.